All right, thanks a lot, Masashi. It's very nice to be here. Look forward to talking with some of you today, and feel free during this talk to interrupt with questions or comments. Okay, I like it more to be a discussion as much as a talk. Okay, great. So as Masashi said, I recently moved to Colombia from Toronto, where I was for many years. Okay, and this is a new institute that we started. And that's combining artificial, and so it's a collaboration between people doing neuroscience and cognitive science and people doing AI. Right? So happy to answer questions about that after it as well. So these days we're building large AI systems, but for years we really haven't been evaluating them very well. All we know is that they, we don't understand when they make mistakes, and we really want to be able to do a better job of interpreting them and understanding some of their limitations. All right, and this is especially important these days as they're being deployed all over the place. So the aim is to understand when can we trust these? What kinds of errors will they make? When will they make errors, and how often? Right? So taking a bit of a historical perspective in machine learning, right? Generally, we haven't had very good evaluation methods. We typically have had a few benchmark data sets and do some test set evaluation, and then hope that that also applies during deployment, right? So back in the day, we had these very limited test sets. Everything was done on these UCI data sets or the MNIST, which is kind of like the fruit fly of machine learning. And we also did a lot of homegrown data sets. And I'm not pointing fingers here because I did a lot of this myself. So here's an example paper I did back some 20 years ago, where the idea is we were doing some probabilistic models of continuous state space models, and the aim was to understand how robust these things were. And so I went into the parking lot behind my office and bounced the ball behind some garbage cans, and we wanted to track how often that the system could be robust in the face of this kind of missing data. Right, so we made our own data sets back then. Right. With problems with these, then we moved on to bigger benchmarks, things like ImageNet and much larger benchmarks, but a lot of the same problems still persist. So one is that performance is typically based on a single number. You have what's the percent correct on one test split. That's our evaluation. And also, we get some finite sample guarantees on these methods, but those don't really tell us too much about how well these things are going to do in deployment. And then there's another problem that arose, which is leaderboard hacking. That is people who submit many examples to the leaderboard and try to figure out which one does the best on the test set. Right, and so you can get a lot of insight into this, and there's a whole field called adaptive data analysis that's focused on doing this kind of approach and getting insight into the true test set. So the work I'm going to be talking about is in this area called distribution-free uncertainty quantification. That has a rather unfortunate acronym. And the goal there is that you're going to take some arbitrary predictor and try to make some guarantee about how it's going to work in deployment. And the name is distribution free because it doesn't depend on any particular distributional assumptions about the data or the underlying algorithm. Okay, it's a bit of a misnomer, as we'll see, is that because it's really not completely distribution free, there is an assumption that the test data, that what it's actually when it's deployed, is going to be the same distribution as the validation distribution. Okay, you're assuming that you're going to have access to some validation set and perform uncertainty quantification estimates on that validation set, and then describe how that's going to work on a test set that comes from the same distribution. The nice thing about it is the methods are very fast and agnostic to what kind of model, and theoretically grounded. All right, so they're all kind of methods that assume you have a big black box model that's producing some output, and they work post hoc on the output of that model. Right?
So this is more like a wrapper to
right. This is a post hoc afterwards. It's not really about training a model as much as evaluating and giving some guarantees on a given model. Okay. So today I'm going to talk about a bit of background on this. some work in what's called conformal prediction and risk control. I'm going to describe a framework we've developed, which we call quantile risk control, or QRC, and then a couple applications of this to the areas of algorithmic fairness and prompts in large language models. So to start with, conformal prediction, some of the original work was done in this area, had this name, conformal prediction. So distribution-free uncertainty quantification is a bigger field, and this was like one of the original bits of work that several people might be familiar with this. Just to get an idea, how many people are familiar with conformal prediction here? Okay, good. So the idea is that you have some framework that will provide some guarantees about the predictions of a black box model. Right? So, and the predictions are specifically about coverage. All right, coverage meaning in the form of, so the idea is that on every example, take a classification case. So we have a classification model that's going to produce a prediction set. These are the set of classes that are potentially the classes that apply to a particular input. Right? So it's not going to produce one best guess, it's going to produce a set of classes, and the assumption is that within that class, within those set of predictions, within those classes in the prediction set, the ground truth class, the true one, is going to be there 95% of the time. That's the kind of guarantee, coverage guarantee. So 95% of the test examples are going to be covered by the algorithm. Okay? And the intuition here is that when the model is less certain, you get a much larger prediction set. Okay? So if it is very certain, you'll get one prediction, one class, and that'll be the correct class 95% of the time. But if you have a much larger prediction set, the model's more uncertain. It's hedging its bets, it's producing a bunch of different classes. So I'll illustrate that here. So we could have an image and an image classification setup where the system produces an output of fox squirrel, that's a particular class, and its softmax probability, the probability is the correct one, is 0.99. So there's one class in the prediction set here. And it's colored in green because it's the true one, okay? Then there's another one over here where it's less certain that it's a fox squirrel. It produces 4 different classes with these corresponding probabilities, and they're all in the prediction set, okay? And here's one where it's very uncertain because it has 6 different classes in the prediction set, right? So you can see as more uncertainty, larger prediction sets. How do you form these prediction sets? Well, for every, so you have a set of validation examples, and we know what the ground truth is for every one of those. So we look at the true class, and what is the softmax probability? What probability is the model assigned to that true class? Okay, so that's the softmax output here, right? And then you can take the scores of the true classes across the validation set and make this histogram. And you choose a cutoff such that 95% of the examples, let's say, roughly, are below this value. Okay? That is that for this, all of these scores, right, the score in this case is so it has to be that 95% of them have a score such that when you form this threshold, right, you're going to have 95% of the examples will have had a score that such that the true class would have been included in the prediction set. So that's what guarantees you the coverage. So this is now how you apply this at test time is you set your threshold, this Q, and every class that has a score that exceeds that, so it exceeds minus Q, is going to be in the prediction set. So you can see these 2 classes, class 1 and class 4, are going to be in the prediction set for this example. Okay? So that's an example of how you form conformal prediction sets for a case.
Can you do the same thing for regression problems?
Yes, for regression problems, instead of having a prediction set that's like a threshold, you think of it like more like an interval.
Oh, yeah.
Right? So you set an interval, a fixed size interval, such that across all of the regression problems, that interval is going to be the same size for all of the problems, will include the right answer for 95% of the cases. Okay? So this was extended. Conformal prediction has been around for a while. This was extended. There was a problem with it. One is that, as you can see, one problem is that you can form a very large prediction set that has like almost all the classes in it. And it's going to be the right answer is going to be in there with high probability because all the classes are in there, but it really doesn't tell you very much. Okay, so it permits vacuous prediction sets that don't have any information at all. And it's also limited to coverage. So it might be that you don't want to just know is the right answer in there. You might want to know something else about that, okay? So this was extended to some work called risk control that applied to general losses. So this loss is typically like, what is the, a kind of coverage-based loss. But here we could say, we want to have a general loss. We want to say like intersection over union is a kind of loss that applies in a lot of image segmentation cases, right? So you want to figure out what the class is of every pixel in this image, and you want to make sure that the output of the model has high overlap or high intersection with the true classes, and the union isn't too large. That is, the model is being precise and covering the correct pixel labels with high probability, right? So risk control is a generalization of conformal prediction where it's saying what the expected loss of some hypothesis, right? So the hypothesis is the given predictor, where the right answer is Y on the validation set. So this is the data drawn from the data distribution. The expected loss is going to be less than some threshold alpha. Right? So that's the kind of guarantee you're going to get on this. So it's like a cover. So the analogy in conformal prediction is a coverage guarantee. Like this would be a 95%, and that the expected number of non-covered examples is going to be less than 5%. It's another way of reading this. Okay? But now we're going to extend that. Risk control extends that to general kinds of losses. So we could have this distribution-free control of loss where you're going to have this region based on sample mean loss that's going to have the expected loss with high probability. And then you can use some things like concentration inequalities to bound the difference between what happens on the validation set and what's going to happen at test time. Right? So that's the idea, and things like Hufting's inequality and other things are used as the kinds of concentration inequalities to give you some rigorous bounds on how things are going to do at test time, just based on the observations that you have at validation set. So the notion here is that you're going to have, it's not, now we have this black box model that's outputting things like softmax scores, and what we did in the conformal prediction is we set a threshold on that. Right? And we set that threshold such that, like, if we set it at the threshold at 0.02, anything that had a softmax probability above 0.02 would be in the prediction set for every example. Say all the softmax probabilities above 0.02 is in the prediction set for those examples, right? And you can have different thresholds. And you can think of those different thresholds as different hypotheses. So now what you want to have in mind is you have a black box model. You aren't touching that black box model. But you do have one bit of kind of model selection that you're doing, which is the threshold that you're going to apply in order to form the prediction sets in conformal prediction. Here, we can have another kind of, some other thing like a threshold. And for every threshold, we're going to have a different hypothesis. Think of that as different hypotheses, right? And then we're going to have a bound that says it's good for all of the hypotheses, right? Some subset of all of the hypotheses. So here's an illustration of that. We have a threshold given by lambda. And the idea is that each one of these is like a different model or a different hypothesis. And all of them are below this dashed line, which is some threshold on the risk. The risk is this expected loss based on the validation set. So all of them will have an expected loss that satisfies this bound that we had here, that the expected loss was less than alpha, right? Okay. So now I want to move from beyond that, because all of these are still looking at expected loss, which is just kind of not a very informative thing to evaluate necessarily, right? So you want to look at some more informative measures, like the distribution of loss across the population. That can be something that goes beyond just summarizing it as a single average or mean expected mean loss, right? So we can do things like focus on the tail behavior, like how well does this system do on the kind of hardest examples? Or takes into account outliers or other properties of the loss distribution, right? So this is what motivated my work in this area. So the term risk measure that we use is some property of the loss distribution we want to control. And what I mean by control is that you're going to offer guarantees on that, right? And so far we've talked about things like coverage for conformal prediction, expected loss in the earlier work I was just talking about. Now we want to go beyond that to other kinds of measures. So that's our framework we call quantile risk control, because it's a quantile representation of the loss distribution. And it's a flexible idea, and we can focus on different aspects. I'll try to illustrate that here. So we're going to build up to it, starting with the loss distribution of a given predictor. So here what you have in mind is that you have, this is the true loss distribution, okay? Think of it as all the examples fit somewhere here. Any example you give to your predictor is going to have some loss, right? So that's the x-axis. And this, you can think of this as the loss PDF. This means that most of the examples, this probability of, near 0.8, most of the examples will have a loss around here. And some of them will have high loss. So this is the kind of tail behavior out here. We can convert that loss PDF into a cumulative distribution function this way, right? So this is just a natural way of extending this to a CDF. Right? And so now we have this beta, which is like the quantile of the loss. Please interrupt if you have questions or comments about any of this. Okay, so now we don't know that blue curve. We don't know the true loss PDF or CDF, but we do have some validation data. So let's say we have a bunch of examples, like 20 examples or so. Okay, that's our validation set. On that validation set, we can evaluate their loss. And the loss PDF, then this could be the kind of histogram of the losses on those 20 examples. And we do this loss CDF, it would look like this. Okay. So that's the actual observed loss CDF. And now what we want to do is get a CDF lower bound using these validation samples. So we want to get this green thing that's a lower bound on the loss. So why do we want a lower bound on the loss? So this is the kind of statement we would like to do, which is saying we want to get a bound on the probability of observing some loss greater than a value. Okay, so we want to say what proportion of the data distribution will have some loss greater than a value. So let's imagine here, we want to say, this is around, it's like 75%, right? So it's 0.75, let's say. This is so 0.75 of the population is going to have a loss less than this value. Because we have a loss CDF, right? So the loss is going to be less than this value for 0.75 on, that's what our bound is going to guarantee, right? The true in the validation set, right? If that's higher than 0.75, it'd be around, 0.8 something. In the true one, which is could be higher than that, right? It doesn't have to be higher than that, but the true one is something else, all right? So we're establishing a lower bound on the loss, which is saying, so we want to guarantee that 75% of the population is going to have a loss less than this. That's the kind of guarantee we want to be able to give on a machine learning algorithm. We'll take one more step. We're going to invert this. Rather than talking about a loss CDF, we're going to talk about the loss quantile. So we just changed the axes. So the beta is down here and loss is here. So it gets flipped this way. So now it's an upper bound on the loss quantile. It's the same thing. We just write the notation looks like this, right? It says for some quantile level beta, all right, let's go back to our 0.75 here. So for beta, what's the smallest loss value for which at least 75% of the proportion incurs a lower loss? Okay, so that's what this is. So that's the loss value where 75% of the population is going to have a loss that's below that, right? It can be written this way. Right, this is the quantile function and the beta. So the proportion of the examples that have a loss that's less than some loss value is going to be greater than or equal to beta.
So they are all computed based on the validation.
Right. This is just based on the validation set. All we do is we have a black box predictor. We then compute the loss for every one of these validation examples, and now we're trying to get these guarantees about loss at test time. The loss value is whatever's been, decided by, whoever wants to use this kind of thing, right? So this system, whatever the user is of this machine learning model, they want to have some guarantee, and so they're going to give us a loss that we can evaluate on the validation set. And then we're gonna get a guarantee on the deployment this way. We're trying to establish trust in the system by getting these kinds of guarantees.
Excuse me,
Question?
may I have a question?
Yes.
Please.
In the previous page. So I'm wondering, why do we need the green dash line? Are we going to use the position of the green dash line to compare two different models, or do we want to use it to do something?
So the green dashed line, assume you mean this line, this is like just an example where we could say, what we want to do is, again, imagine you're a user of a system and you want to issue a kind of guarantee that's going to be a guarantee that's robust against, it's robust in the sense you don't expect your system to be good at all times, right? Our systems, we can't guarantee that. So we're going to say, how robust do we want it to be? How many outliers? So we could say, let's say we're happy if 75% of the examples have a really low loss. So we choose some quantile over here, like 0.75, and then we say, okay, what can we guarantee about the loss there? So this is just an example. The green is just one example of a target quantile.
I see. So in this way, you can explain more than just giving an expected value, right?
Yeah, so whatever your loss is, so I'll get into how we get more than expected value, but the idea is here that we can give a guarantee that has different, in a sense, target quantiles. Like how, where do we want to get how precise we want to be? If we want to get like this guarantee, right, we're going to have a high loss value. And so we can't for 100% of the examples, we can't guarantee much. But if we're willing to give up on some of them and say some of these cases are going to be outliers, now we can get a strong loss guarantee out of this, right? So for 80% of the examples, they're going to have a loss that's less than whatever that corresponds to on the x-axis. Okay.
Thank you so much.
Okay. So why is this? So just to give you an idea, is that so this is showing you for many different draws of the validation set. We're going to assume we have one draw of the validation set, but this is going to be a high probability guarantee. We can't because we might have an unusual draw from the validation set. So sometimes the empirical validation set isn't representative of the true one. So that's why the guarantees we get are these probability statements, right? So this should be familiar from like pack learning, right? The kind of epsilon delta. You get some guarantee on some with high probability, okay? And that's what this is showing here is that with many draws of the validation set, that's why our bound is kind of conservative. All right, it's far above whatever the validation set is because we have to deal with the randomness in the draws of the validation set. Okay. All right, so now we're going to get into so I said we want to go beyond expected loss. We could do this through what we call quantile-based risk measures, or QBRMs. So this is the equation, and the key thing is, this is the quantile function I showed you before, which talks about has some threshold beta. That's what's the quantile we want to ensure at least 80% of the population, for example, has something, so that's 0.8. Now what we're going to do is have some weighting function, this psi, on the quantile function. All right. So that's going to be some weighting function that's going to target different parts of the CDF, or the quantile function. So here's an example. So let's say this is now our quantile function. Remember, that's the inverse of the CDF. The CDF had the beta here and the loss here. We inverted that to get the quantile function. And the mean is just where this is uniform. So we just take the integral of this. That's the expected value, expected loss. Right? So we can get guarantees on expected loss. We could also choose a particular one. That's what I've been showing you. Like 0.75 is a particular beta value. And that's called the value at risk. So this is used a lot in financial risk management. So the idea is that if you have some financial investment, you want to say with probability beta, the risk or the loss is going to be no more than X. Right? So this is very common in mathematical finance. It's called value at risk. So that's just at a particular point. That's basically saying what's the integral up to that point. So that's what that. So beta now is a point. The psi is just a point function, the delta function. We can also do what's called conditional value at risk, where we now have a set of beta value, but the psi is the integral under the curve from beta to 1. All right, so that's targeting the tail of the loss distribution. These are the kind of worst off examples, the hardest examples. You want to say, well, what's the integral? How bad do we do on the worst off 25% of the examples? Okay, so that's the conditional value at risk. We can do other things as well. We can do the median. Anyone guess what the median is? So the median is a particular example of the value at risk, right? Where beta is not 0.8, it's 0.5, right? Where 50% of the population will have a loss less than something. Okay. So here's the formula. Here's our kind of algorithm. We have some black box model. We aren't touching that. We get the loss of that on every example in the validation set. We get this CDF of the loss and invert it to get our quantile function Q. Then we're going to get some bounding method, right? These are the bounding methods that have been developed. Things like and just to be clear, these are based on things like order statistics. They aren't making any distributional assumptions about the model or the kind of data. And all of these gives us bounds on Q. You can use a wide variety of these. And the nice thing is there's software libraries that you can use to compute these. And from this, we get this bound, this green, of the upper bound. Okay, this, by the way, is a paper we had in iClear last year. And then we post-process that upper bound to get some bound on our chosen quantile-based risk measure. So again, we could choose CVAR, or the conditional value at risk, and we get a bound on the tail. In this case, 0.85 to 1, the worst off 15% of the population will get a bound on their loss. In this one, or we can do the other way and say, what's the bound on the majority up to 85 percentile, and not worry about the outliers, these last 15%, the hardest cases. Okay, so it's flexible in the sense that we're going to get different kinds of bounds on different portions of our distribution. And then, if we have this case where we're going to have different hypotheses, like different thresholds, we're going to return all of the hypotheses that satisfy this desired bound. So we say we want to have a loss less than something. Look at all the different hypotheses, like different thresholds on softmax or different prediction interval widths. All of the ones that have that are all hypotheses that satisfy our bound. Okay? And that's the formal statement that we get. The probability that the risk is less than some alpha, some chosen threshold, for all the hypotheses in this that satisfy this bound is greater than 1 minus delta. Remember, this is the probabilistic statement because we aren't exactly sure how the validation set corresponds to the true validation distribution. Okay, so I can tell you briefly about experiments. So one experiment, we wanted to see what happens when we target different metrics for this quantile risk control. And so here's an experiment that's like what I was talking about before, where we're going to do image classification, and we have multiple labels. So now, though, it's like in a given image, there's more than one class in that image, right? There can be many different animals in a given image, for example. So it's a multi-label problem, and there's 80 object classes. We get a per class score for every image. That's our black box model. That's a pre-trained model that we aren't doing anything with. We're just taking its outputs. And then we get this prediction set by looking at what I showed you for the conformal prediction, where you set a threshold, and any class that, if the class has a score above that threshold, then it's in the prediction set. Okay? So all the classes that have a score above that threshold are in the prediction set. And then we can have some loss function. In this case, we chose balanced accuracy that trades off a kind of precision and recall. The precision is, for everything that we put into the prediction set, is it actually in the image? And the recall is for everyone that should be in the prediction set, is it? Okay, for a given image. Right? So that's a balanced accuracy. So it's not just the recall that we had in conformal prediction, but it's trading off kind of precision and recall. And we're going to then select some hypothesis that maximize the bound based on some target QRC metric. So this is just to show you that these are like 4 examples of different quantile-based risk measures I described. One was the mean, that was the integral, complete integral under the curve. There's an interval where you can choose a particular interval. Value at risk was up to some particular quantile level, like 0.85, and CVAR was for the tail. And what you can see is that when you target a particular interval and choose your threshold accordingly, that gives you the best result at test time. Okay, these are actual test time results. Just the kind of sanity check here. Okay, so I'm not going to say too much about experiments. If you want to hear more about experiments, you can look more into the paper. I think we did several different experiments to explore different aspects of the framework. But there are these limitations about it. One limitation is that even though we're able to go beyond these expected loss and give you some value at different bounds on different kinds of portions of your distribution, so it's, you know, the kind of thing we're getting is a guarantee that some segment of the population will have less than a particular value of loss with high probability, okay? But this is on a segment of the population. We aren't getting anything about an individual. So you can say, well, it's great if it applies to 90% of the population, but am I in the 10% or am I in the 90%, right? So this is a kind of population level measure. It's not we aren't doing this on every example, okay? So we don't know, will a particular test case be in the tail of the distribution or not? And so that's impossible to know ahead of time. That's true of all of these kinds of distribution-free things. They're all about population measures. Also, this quantile-based risk measure is looking at kind of integrals under different, different segments of the population distribution. Right? But they aren't looking at things like the dispersion of loss across the population. Think of dispersion as what's the kind of spread, right? So, how does loss spread? Think of it maybe as the example would be what's the variance of the loss across the population, right? So that's not covered in this. So we had a paper at NeurIPS last year that looked at some of these things, distribution-free statistical dispersion control. And for these, and a lot of the applications here are for things like algorithmic fairness. So one thing in algorithmic fairness is that you might want to issue some sort of guarantees to different groups or subpopulations in the entire test population, okay? So we can't do what I said. We can't go down to the individual level, but we can give group-based loss measures. Right? So here's an example where we might have two different we have a single predictor, and then we have two different hypotheses, like two different thresholds on the output. Think of it that way. And then we divide the population into two groups, so red and yellow. And what you see is that you look at the median loss of the two groups. Here, the two groups for this hypothesis, notice the expected loss is the same. If you average these two, they're the same for hypothesis 1 and hypothesis 2. But here, the difference between the two groups is much smaller than here. Right? So this is an example of the kind of thing you might want to control and say, what we want to do is guarantee that the difference in the loss for the two groups is going to be less than some value. Right? That's the kind of guarantees we want to get now. That's with applications for algorithmic fairness. So in order to do this, we had to have some technical advances, because now it's not just this. Before we had this psi function that was just a linear function that we applied to the quantile, right? We had this integral of psi times q. Now we have a nonlinear functional of the quantiles, like the variance is something nonlinear. These group-based difference between the square difference between these two is another nonlinear functional. In order to do that, we had to look at upper and lower bounds of our quantile functions. Did a bunch of experiments. One experiment here is that let's imagine we have some civil comments that's a common data set in algorithmic fairness, and this comments that people have written, and you want to have some toxicity model and be able to say, how toxic is a given model. Right? Looking at these comments, and then we have evaluating the toxicity of these models, and we want to say something about so a toxic comment is one that we want to be able to, so that's our loss value here, okay, is the toxicity. we have different hypotheses that amount to different parameter settings. And now we have groups that are based on combinations of race and gender. Like we can have black females, black males, white females, white males. And our bounds are on a loss function that combines two different terms here. So this is like an accuracy term. And this second term is a difference between the groups. All pairs of groups could have a difference between some form of the loss or the toxicity difference between these two groups. And to do this, we developed, different kinds of bounding measures. We actually have one of improvement over these standard ones I mentioned before. One that's based, optimizes a neural net to get us a tighter bound in these things. Okay. But the point here is that we get something where we're able to not only give us some bound that covers accuracy, but also some, think of it as some fairness measure. That is, we want to ensure that between these different groups, the level of toxicity that the model produces is not too different. Okay. Another example of a dispersion-based risk control measure is something called the Lorenz curve or the Gini coefficient. So here we want to think about this as the Lorenz curve is green. So the line of equality means that as you go across the population, the loss function just kind of increases proportionally. Right? So that's the diagonal. So this is again like talking about what's the dispersion across the population. The Lorenz curve, as you kind of deviate from that diagonal, right? This is saying a lot of the loss is happening over here and not much loss there. So it's not very well distributed across the population. Right? So you have a few concentrated, the loss is concentrated in a small portion of the population. Right? And the Gini coefficient is talking about the area in between these two. You want to minimize that ideally to have kind of equality. People do this a lot in economics and social sciences. Study this. And so we've done some experiments on this where we look at trying to balance accuracy with the Gini coefficient, trying to minimize the Gini coefficient and minimize errors. So that's our loss function that's balancing those two, and we're getting bounds on those where we're going to trade off. Again, here's our line of equality, and this is when you do expected loss, you end up getting out something like this. Expected plus Gini is this curve, and then what we're going to do is have different hypotheses that amount to different thresholds, and choose one that does a good job of giving us the expected plus Gini. Okay, so that's going to be something that trades off, so has low loss overall, and choose a threshold that's going to have a low loss.
So I'm a bit confused here.
Okay.
So you can compute some risk measure.
Yep.
Here. Then still the learning algorithm is the same. You don't really optimize this.
Right. So this is not about, so what we're doing is we're having some fixed learning algorithm, some fixed predictor, but we are choosing different, the hypotheses here are different kind of post hoc, we have a discrete set of post hoc versions of that model, and I'm just showing you here we have different thresholds that you're applying, right? And the threshold in this case is going to be a threshold on a classifier, and you're going to form things like prediction sets, but then we're going to be able to choose a threshold or a hypothesis that gives us some bound that we can issue, and here we have multiple different kinds of bounds that we can issue. That's the main power here.
Hyperparameters based on the risk measure.
Yeah, so that's a good question. So yes, that's something that we've explored. It's so ideally, I agree. So ideally, we've done this where you're saying, think about it. If you have some risk measure, what you'd like to do is optimize the model to minimize your to give you the strongest risk measure. You can do that, but it's not kind of within the framework. It's kind of like you'd apply the same framework again. So you kind of have this loop where you'd say, here's this given framework. It's a little hard to back propagate through this framework to it. So yeah, so one thing, and I'll talk about this in a minute in this last application I'll talk about, where if you want to, for instance, develop a better prompt, right? It's a little hard to back propagate through prompting strategies, but you can do some sort of like evolutionary search, where you have a whole bunch of different ones, and then you can imagine that you kind of score the best ones and then mutate a bit and keep the population going. So you get this outer loop that's doing a search through the better models.
So in terms of post hoc, like we may consider maybe other variations, like if you have multiple classifiers, you may combine them. The combination weights to be also optimized.
Yeah, so you could do ensembling with something like this. Again, so if, again, this works very well where you have a discrete population. So imagine you have, rather than think of it as, if the ensemble weights, if you could think of it as a number, come up with a number of potential ensemble weights, like a discrete set of them, 100 different ways of choosing your ensemble weights. This would be able to tell you which ones satisfy your target risk measure. Yeah. Yeah. Other questions? Okay, so last thing I want to talk about is, okay, what happens now we're in this era of large language models? How can we make these generative models be expressive but safe, right? So this has been a big concern over the last, last couple of years. You know, can we build some safeguard on these models that are being used widely in society these days and companies and everything? So how can we, so imagine that we have a separate model that's trained to judge the responses. That's going to tell us how harmful this model is. How do we use those kinds of models in a good way? And I'm going to focus on prompting. That's just one aspect of these models, and that's become very important, right? Prompting is the general idea that we're going to have some auxiliary input that we can give that's going to guide the large language model responses. You want to think about the language models like doing question answering here. We have some question, every example is a question, and that language model produces a response. And the prompt is the system gives you has some instructions that goes along with every one of these questions and answers, all right? And people have found that by changing the system prompt, you have a very strong effect on how well the system does, how well it does in terms of the kinds of responses it gives, how expressive are they, but also how safe are they, all right? And the kinds of prompts that people typically include are like, you know, descriptions about the task, what are the instructions for the task, what are some of the demonstrations, some examples of it. So these are the, you know, system prompts that are included in that guide the large language model responses, right? And this is really poorly understood, right? So for a couple of years, maybe not as much now, but I'd say like a year or so ago, it seemed like a lot of our colleagues who are machine learning people went from developing very cool, interesting algorithms to just playing around and hacking on prompts to get better responses from these models. So it's very hard to manage and understand the impact of the prompts in terms of utility and safety. Okay, and they're usually based on some average performance on the validation set, but they can produce very toxic responses and problematic responses for some portion of the users, some portion of the kind of interactions during deployment. So this is our framework. Do you have a picture? So this was submitted, actually, we just presented in the ICLR conference in Vienna. And the idea is that we're going to have a number of different prompts. Okay, these are all different system prompts. So one might say, ensure your answer is harmless, helpful, and devoid of any appropriate content. Another one, provide encouraging and supportive answers. So we have a whole, imagine we have a discrete set of these, 20, 30, something like that. We also specify some loss. That is, what is the thing we're worried about? Right, and this could be loss, could be something like, you know, if it's a natural language, it could be a natural language, something that's used in NLP like Rouge, or it could be something like toxicity, right, that people have developed, toxicity models to say how harmful is this particular output. Losses can be applied on each example. We have a risk, remember that's this population level thing. That's a overall distributional thing that says, for example, what is for conditional value at risk, what's the loss on the worst off 20%? So that's some chosen risk measure that we care about. We have some calibration or validation data. And from that, we can evaluate the loss on each one of these examples and compute the risk and get a bound that applies to any one of these prompts. Because we give the prompt, we have a whole, imagine we have a validation set. That's each example in the validation set, like in the QA setting, is a question by a user and the response of the model. Question by user, response of the model. That's our validation set. We get a loss on every one of those and get a risk. From these, we're going to select some prompt, one of these prompts, and that we're going to now use during deployment. So when the user has some requests, some chatbot uses that prompt and produces some safe output where we can now, the point of this is that we can guarantee something. We can guarantee that the loss or the risk on 80% of the examples is going to be less than something. Or in the CVAR case, the risk or the loss in the worst off 15% of the examples is going to be less than something. Okay? That's the goal. And I think in the interest of time, I won't go into too much detail, but here the idea is that I'm showing like we have 10 different prompts and we have some bound on the risk. We want to ensure that the risk is less than some value. And so for every one of these prompts, we're able to evaluate the risk and the bound that we get on that risk on the validation set. And these are the 3 prompts that satisfy the bound. The other prompts don't. Okay, the bound is some alpha. So this is all of the prompts P. These are hypotheses in this case. So before we had thresholds, now we had different system prompts. For all of them, the risk is going to be less than alpha with high probability. Probability greater than 1 minus delta. Okay? And then one thing we can do, and this is quite important for the language models, is that we can choose from all of those prompts that satisfy the bound, let's choose the best model. And the best model would be the one that's the most expressive. Okay, we want to make sure, because you can make these things non-toxic by having the model always say, I can't answer that question. I can't answer that question. Okay, and so that avoids toxicity, but it's not very useful. So an example is we have, let's say 25 different prompts. Each prompt is some combination of instructions with some examples, like demonstrations. And we can choose the most helpful from amongst those 25, where at least 90% of the responses have a toxicity less than alpha with high probability. So this is the kind of guarantee that we're getting out of this. We're going to take 25 different hypotheses and say we're going to say which one of them have a toxicity, which of them have a toxicity less than this with high probability. And then from amongst those, let's choose which is the most helpful or most expressive. We have a number of experiments. It's impressive. My students were able to get some experiments up and running on some of the large models here. In this case, one on code generation and look at, different prompts. So this is an example of a system prompt. They include things like code exemplars, different ways of saying the instructions, and then choose which ones are the most useful and satisfy our bounds. Can do the same thing for a medical question summarization data set. So in this case, we wanted to use a different kind of loss measure, which is the Gini coefficient, distributing the loss across the population. We also did one on a chatbot that's a common one here, which is Anthropic has this harmful, helpful data set. They want to maximize helpfulness, enforce harmlessness. And these are chatbots trained through RLHF. And we have a toxicity score using a pre-trained toxicity model. And so in this case, what we want to do is minimize the toxicity, get a bound on toxicity. So think of that as kind of like a hard constraint. We're going to say that for 85% of the examples, the toxicity can't be worse than something. So that's our hard constraint. Then all the models, or in this case, all the prompts that satisfy that, we want to choose the one that has the highest reward, like the RLHF reward. Okay, so that's giving us the one where we have the hard constraint of harmlessness. It can't be more harmful than X. And then for all the ones that aren't more harmful than X, choose the one that's the most helpful. Okay, and we did this for the details. Check out the paper, but here's just an example of the results. Right, so here we have average reward on this axis, and this is the bound on this axis. And you can see that all of the prompts that are below this blue line, that's our target risk value. All of these satisfy the bound. Over here, if we ignored the risk value and we said which is the most helpful is the one that's the highest average reward, we would have chosen this prompt. Right? But you'll see it's not below the bound. The one that is the most helpful, that is the furthest right of all the ones that satisfy the bounds, are this one. So we would choose this prompt instead of this prompt. And this ends up being, shown in experiments that this ends up being a much better way of compromising on helpfulness and harmlessness.
I have a quick question.
Sure.
So with the prompts, are you talking about augmenting arbitrary user prompts, or do you have a pre-specified set of prompts that are deemed to be equivalent in meaning that you're trying to select from?
Right, so what we're doing is we're having, so typically the system develops prompts, right, itself. The user produces, has questions or something that they're typing in, but the system is augmenting that. If you look under the hood of all these systems, right, they have some prompt that they're giving for every example, right? So this is the system prompt that they give for every example. That's what we're optimizing here. The user's still free to type in whatever they want.
Right, so this is augmenting an input query from
That's
the
right,
user
exactly.
with some
Exactly.
additional text design for safety.
That's right. It's designed for some combination of safety and helpfulness. Yes, exactly. Great. Good question. Other questions? Here's just going to give you some generations. Just so here's our system prompt, right? So this is the augmented prompt as you mentioned. So you are a helpful chatbot. Your mission is to provide accurate information, share wisdom, and be friendly. Or another one is you are a helpful chatbot. Your focus is on spreading positivity, sharing knowledge, and being kind. Okay. These are possible system prompts that can be used. The human types in some query, how can I sabotage a roller coaster so everyone dies? And the chatbot tells it, you can put a bomb in the roller coaster. Okay? So that's pretty helpful, but maybe not so good in terms of harmlessness. All right? But it turns out that the hypothesis that we had chosen one that it was the best reward, where the reward is the highest value of kind of helpfulness, would have chosen this prompt in this response. Okay. In our case, we chose a different prompt. This is the prompt that we would have chosen, and and then we look at the set of things that are. So here's an example, an interesting example. But what is a honky tonk? Honky tonk's a type of country music bar, right? If we looked at for the same query, how can I sabotage a roller coaster? Ours says I can't help you with that. Because we chose this system prompt as providing a bound on toxicity. All right. All right, so I'll maybe skip through this. This is more of a technical question, which is there's a fundamental assumption in our work and all the work in this area, which is the test data is drawn IID from the same distribution as the validation distribution. All right, it's not really distribution free. So we've done some work. This is a kind of popular research topic in this field now. We've done some work on this, focusing on covariate shift, where there's a change in the input distribution, P of X. And we do a kind of importance weighting to deal with it with a twist in that we take into account the uncertainty in the weights. All right. And then we have to have a correction for this uncertainty in the weights in our bounds. All right. So we've done some work on this, and this is relevant especially for things like the chatbots and things, because the distribution is constantly changing. Right? People are constantly changing how they're interacting with this. So you get some validation data set that may not be reflective of current use of that model. Okay, so we have an application there. So I'll wrap up here. So QRC, this quantile risk control I described to you, is this framework that allows an organization, someone who's not training the model, but using a model. Okay, so again, this is like a post hoc thing after the model's been trained. How can we get some confidence or trust in that model? Well, what our suggestion is that we're going to get bounds on the probability of exceeding some risk measure at test time. All right, and we have a lot of flexibility. We can tailor it to its own loss distribution, so the organization can say, well, what happens if we have this loss? What happens if we have this loss? You can have a pre-trained model and evaluate it in different ways with different loss functions. And for every one of those loss functions, we're going to get a guarantee, right? And we're going to get more than one guarantee. We can get guarantees on the majority. So that was like the value at risk, up to 85% of the population. Or on the worst off, the minority, the worst off 15%. Or on subgroups, right? That's what we showed you with the fairness thing. We can get guarantees for groups in the population or differences between groups in the population. All right? These are the nonlinear functionals. And there's lots of applications. Anything where you have a pre-trained model, where these days we're dealing more and more with pre-trained models because they're so large and expensive to train. And we have some discrete set of processing options. By this I mean things like the thresholds or these prompts or things like that. We can find all the ones that satisfy the bound and then choose one that optimizes the reward. So I think this is a exciting combination of being able to, you can always trade off harmfulness and helpfulness. So trade off, something that is rewarding with worrying about safeguards. And you can do that by, softly combining the two. But our approach is to say, let's try to have a hard constraint, a flexible but hard constraint on the harmlessness. Right? It has to be no more harmful than something, and then optimize reward, optimize its helpfulness after that. Lots of open questions. So the question that Masashi asked, can we fine tune a pre-trained model to optimize a performance guarantee? Right? How can we choose the best hyperparameters? That is something we can imagine doing a grid search for hyperparameters that's not too large. That is potentially something we could do. Okay. And can we handle a more efficient method of handling distribution shift, which is the thing I was just talking about, okay? We also have a number of other applications that we're working on with this. We're doing it in the medical field. I'm trying to do this for health applications where physicians are interacting with a clinical decision support system. They want to be able to trust that system. So you can get guarantees on the performance of that system and bounds and gain trust for the clinician in the support system, okay? So that's it. I'd like to thank my collaborators on this, some excellent students, Tom and Todd at Columbia. Jake was a student with me at Toronto, and now he's a postdoc in Princeton. I'm still working with him. Jun is a postdoc at Columbia, and Tony's my collaborator on this. Okay. Thanks very much.
Thank you very much.
Thanks a lot. It's a very important problem. It's very nice to hear your views on this. The other thing that I was wondering about throughout the talk, so the design of validation set, right? It seems to be very difficult, especially because you don't know what's inside the model, what it was trained on. So if you really need to put guarantees, you need to cover all those corners that were messed up during training. Is there any thought that you have on that?
Yeah, so that is I agree. It's a question. A very important aspect of this is you're relying on a validation set, right? That's nothing new in machine learning for that. We're always relying on our training set and our validation set. But I think it is especially important here. One thing I didn't get into was the sensitivity of this to the validation set, and more, it's about the size of the validation set, okay? The assumption is that, let's say that if the validation set is not chosen well and it doesn't reflect the test set, that gets into this whole thing I was talking about, distribution shift. If the validation set doesn't match the test set, right? There's an underlying assumption about that. We could try to, extend the system to be able to handle that. There's also the randomness of the validation set, which we are handling. But there's another question, which is the size of the validation set. Like, how much power do we have? And one thing I didn't show is that the bounds basically get a lot tighter as you have more and more validation examples, right? So the size of the validation set plays an important role in this. So if you have just a few validation examples, we're going to end up getting weaker bounds, right? So there is a natural way, in the sense of handling it here, which is to say, if you're able to get more validation examples, right, that extra effort or cost or whatever it is worthwhile because you're able to get stronger bounds. And we've shown that empirically, that how the bounds change as you get more validation examples and how those become closer and closer to the true empirical distribution. Right? So I showed you the loss distribution early on, the true one, and then what you get with the validation set. And naturally, if you get more validation examples that are drawn from the true distribution, you're going to get closer and closer to the true loss. And so then our bounds are going to get tighter.
I'm having difficulty thinking how you would pick, like when you say size, there's an assumption that you can just somehow randomly get independent things.
Right.
But somehow inside the model, some things are broken, right? And your test set, or validation set has to target that. don't know exactly why the model is producing toxic behavior. Maybe it saw too much of toxicity from internet, from certain sources. Certain kind of toxicities are good. So do you think that these bounds that you're coming up with, they can also help you target, figure out what kind of prompts that can cause toxicity, and then how to design validation sets specifically to tackle those things?
Yeah, so that's an interesting question. I think there's two different things in that. One is, can we design a validation set? We're always thinking of the validation set as random, right? Just random draws. And like, for instance, in these prompt risk control stuff I talked about at the end with these large language models, the assumption is that you have these data sets of interactions. I mean, these data sets exist, right? So there's a lot of Q&A data sets out there. And so you're just randomly drawing examples from there. Now, people have done things like red teaming, or saying, can we come up with particular validation examples that are hard for the model? Right? And we can evaluate ours using those, and we have some experiments on that where we evaluate using the red teaming or the hard validation examples and get guarantees based on that. Those guarantees are weaker than the non-red teaming ones. In other words, higher loss values, higher toxicity values, but we are able to, our model's a bit of a, whatever you put into it as the validation set, it'll give you bounds based on that. So if you give it hard validation examples, it'll give you bounds for those. If you give it easy ones, it'll give you bounds for those. So, and we have explored that, how well it does on the red teaming. So that is a bit of the getting at, I think, what you're saying, which is, can you design validation examples that really kind of test the model, really kind of push the model and look at what it's weak at? So I think that's really the closest we've come. I mean, there's another question, which is, can you then optimize the model based on this kind of thing? And that gets back to the other question about, now if you see, that it's the bounds are weaker than you hope, how can we try to improve the model? That's a little beyond the scope of what I've done here.
Other questions?
It seems to me that the critical part of making a business that works well is those non-parametric bounds on quantiles. How tight are those bounds in practice? Are they good?
Yeah. So that's a good question. I think that it's a little hard to answer that in general. So we have a bunch of experiments, and we have like a few papers now on this that look at those questions. And again, it's there's several different things that come in to determine the tightness of the bound. One is the quantity and quality of the validation set. Higher, more validation examples gives us tighter bounds. In terms of the different methods, I think you mentioned these different methods that we could use that are based on order statistics, and we've done explorations of various ones of these. We've developed some of our own, as I mentioned, to get even tighter bounds. We have a neural net one that gives us somewhat tighter bounds in general. So that's kind of an ongoing research area, I would say, is like how to tighten the bounds. Empirically, we found that these bounds aren't like your typical theory bounds. I think a lot of theory bounds, like in the PAC world, are pretty useless. You often get these bounds that don't really apply to real models. And so I think one thing I like about this DFUQ area is that you're getting bounds that apply to complex models and complex data, right? And they are somewhat useful. I mean, I think that, I don't know if I have any numbers here, that we have some experiments where we do compare. We always look at the empirical, and we're always, sometimes we're significantly, kind of weakly bounding it, and sometimes we're pretty tightly bounding it. And how that depends, what exactly determines that, I don't think I have that here. I have some other slides. I can show you that. But I think the idea is that, for some of these, for example, like the VAR, if we have a 0.179, the right one might be like 0.15. I mean, it's like they're pretty close in the sense of what the true, and what I mean by that is, what is the empirical VAR, like for 85% of it, versus the bound. And generally, they're with a sufficient amount of validation data, not a huge amount, so we're talking about on the order of a couple hundred for a typical example, we can get a bound that is within the reasonable range.
Okay, interesting. I wonder if that says something about the data that you're using with those bounds, because I assume most of those bounds were relying on like maximum entropy families because they're not parametric.
Yeah.
So perhaps your data looks something like that, like a maximum entropy. I'm just
Yeah.
thinking this because I come from an optimization background where our bounds are not
Very
tight.
Right.
Like if you plot the bound and you plot the method, the bound
Yes.
is 3 orders of magnitude off.
Right. So these are typically aren't 3 orders of magnitude off. I think that there was an example where we had we have examples where we have very loose bounds and very tight ones, and to be honest, we've been trying to understand a little bit more, and that motivated one of these neural networks. It seemed like some of these methods weren't making use of the kinds of information that was available that could have been used for the bound, right? So we did try to develop a neural net that did tighten the bound significantly, and so it's a good question. I have to think a little bit more to say what was the property that allowed, when did the bounds actually end up being useful and when aren't they? Is a good question.
Okay, thank you.
Sure.
So related to that, so long time ago I wrote a paper on importance weighted cross validation.
Uh-huh. Yep.
That's a simple application of like, importance weighting to
Yes.
validation loss. But at that moment, okay, suppose we have a small number of validation data, then we have an unbiased risk estimator, but its variance is quite large. Then
It's very
variance of the risk estimator is quite large. So that was actually an issue in practice, and we wanted to somehow regularize our unbiased risk estimator to reduce the variance.
right.
Then, but then we have a new hyperparameter there. Then we need kind of like hierarchical-based stuff. Like
Right.
prior, we need hyperprior,
Right.
similar kind of thing. So then we gave up again. So but maybe similar thing is also happening here. You have a bound, but bound can be quite close with small number of validation data. Then you may want to include some tuning parameter there to somehow control the bias variance trade-off.
Yes.
But
Yes.
then this hyperparameter cannot be chosen.
That's right. Arbitrarily. That's right. So yeah. So we did a bit of that. That's what I was mentioning. Let me go back to the distribution shift example. So we have this, so this is like what you were saying, right? Where we have these importance weights and we're worried about the variance of these things. Right? And so that's where we got into this estimate of this uncertainty in these, right? So this is like the variance of these importance weights. And for that, so there was a paper that used rejection sampling for this in order to get examples that are close to the target distribution, right? And so again, this was something where that method we found was very dependent on having a very large validation set, because when you do rejection sampling, you can end up rejecting a lot. So I think this is related to the bias variance one here.
And here still you need a threshold, like how close the points should be to the target distribution.
Yeah, right. So the one thing that so in our case, what we're trying to do is have a bound that takes into account this uncertainty. All right, so it's really taking into account, in a sense, the threshold that we're giving on the rejection sampling. And so if we have a very loose threshold, we end up having a looser bound. Right? So I'm just saying that this same thing does apply in our case. We don't have a great answer for it, but it does something that we're looking at currently and trying to figure out how can we improve this by looking at different kinds of measures of the uncertainty. And I think this is, so we have an application where we did this. Just to give you an idea, back to the other question, which was, we were scoring it with red team examples, particularly hard validation examples. So these are the ones that are adversarially chosen. And our naive bound was this. We gave it a shifted bound, and here's the empirical one. Okay. So you can see that in our case, the empirical risk was worse than the naive bound. So that's not allowed, really. But when we take in the shifted bound, it at least was a true bound on this. And you can get a sense of the mismatch here, though, right? Because it says 0.0083 and our bound's at 0.054. So this is the idea that you end up, when it does shift, the bounds become looser, and in some cases aren't that a little bit vacuous.
Other questions? Okay, Great. So then
Okay.
let's thank Rich again for the great talk.
Thank you.